Welcome back. So let us continue our discussion on this momentum theory and the extraction of the power coefficients and all this. So what we discussed in the last session, that is that what is the maximum power coefficients, which is essentially the theoretical base limit, and then what is the thrust coefficient or maximum thrust coefficient that is possible. So these are optimal. So, but what happens is that though we have got this CP max is 16 by 27, but theoretically possible rotor power coefficient, but in practice, three effects lead to decrease in the maximum achievable power coefficient. So there are effects which does not allow to achieve this coefficient. So one is that rotation of the wake behind the rotor. Number two, finite number of blades and associated tip losses. Number three, non-zero aerodynamic drag, because drag is not zero. So this is what. So what happens in that case, though we have that maximum power coefficients theoretically supposed to be 16 by 27 or so what happens is that the overall turbine efficiency, becomes a function of rotor power coefficient and mechanical, including electrical efficiency of the wind turbine. So it becomes an overall efficiency now becomes an. So what it does that eta overall becomes P out half rho A U naught cube. So this you write eta mic into Cp. So the output power that you get, it will have eta mic Cp half rho U naught cube. So that's what you achieve. So in practice, there could be losses, and because of the loss, so you kind of, and those are possible because there are rotation of the wake behind the rotor, there are finite number of blades which could have. So the momentum theory analysis that we have carried out so far, it assumed no rotation, which was important on the floor. Now what we can do, we can extend that analysis where the rotating rotor generates angular momentum which can be related to rotor torque. So that means what we want to do now, we want to include the wake rotation so that in our calculation that is something we can incorporate. So what we do, we use this wake rotation and rotor disk theory. So what you have, so again, this is connecting with the picture where we have considered the turbine or positioning of the turbine with the reference position and the other position where you have. So what we have this similar picture where the turbine is there, but here we are looking at one particular aerofoil and considering this rotation. Obviously, here we can actually have tip speed of, then this is R, and let's say this is omega, this would be R omega. So if your speed at any R which is less than R would be R into omega. So omega is 2 pi by T, where T is the period of rotation. Okay. So that's what you have. Now, what you, so air, when it is going through this rotation, air is deflected in the tangential direction by the blade. So air is deflected by the blade in the tangential direction. So tangential, now we define tangential induction factor or tangential induction, which depends on R and this tangential velocity V1 tangential. So this particular picture now, along with the position where you can see this is the airfoil, that means the blade, and this is the airflow, and then blade is rotating like that. So which kind of tells you a situation. I mean, like if you look at that, that means this is the aerofoil and this is the air coming in, and blade goes in a rotation like that. And that is why this R omega in this direction, which is shown here. Okay. So it's primarily the matter of velocity triangle, how you kind of come across this thing. Tangential induction, the tangential induction which depends on R dot V1 and the tangential induced velocity is equals to V1 R omega A prime. So we define here A prime as tangential induction factor. Earlier we have seen the axial induction factor. Now since we are considering the disk rotation, so we are taking into consideration the tangential induction factor as well. So the tangential induction factor would come into the picture. Now, so here in this particular picture, as we see, with an initial tangential velocity, which is here, when the air is coming towards the rotor blade, that is 0. the tangential velocity downward, which is going to be v3. So we can estimate that. So tangential velocity downward is v3, which is r omega 2a prime. So the change in tangential momentum would be m dot v3 minus 0. So that is what, because the initial tangential velocity is 0 and at the downward side it is v3. So if you see this particular plot, which clarifies a lot of things, actually what happens is the like air pushes the blade. So essentially these are the rotor blades airfoil which is shown here. So there would be blades and the air is coming through these blades are rotating like that. So air pushes the blade upward because of this is happening because here you get this resultant lift force which pushes this to rotate and the air is deflected downward. Okay. So that's what this rotational aspect of it, or the rotation of this disk has been brought in to encounter the losses due to this disk rotation and all these things. So what you see that now with this we can now move to find what we can find is that we can find or we can now compute V3 of R for given A omega R u infinity, obviously all these things. Okay, so based on, so here we consider an infinite simal annulus of area dA. So infinitesimal annulus of area dA, and we see this from the center at R, that will be small dr, and the complete radius of the rotor is R. So here dA is 2 pi R here. Okay, so that's what you have. Then what you get now, if we, so now we'll continue with the same numbering system. So this is 16. Then what we can write is that 0 to R, 2 pi R dr is pi R square, which is 17. Then we can have the infinite simal power extracted, that is dp half rho u infinity cube dE into Cp into. Now to harvest this power via rotary motion with the angular velocity of omega, we need a tangential force of dF. Thus, what we can have dp equals to df r into omega. Okay. Now, since F equals to m dot delta v, which is due to change in momentum, and where my m dot is rho a u infinity 1 minus a. Okay. So what we can have or can write df equals to rho dA u infinity 1 by a v3 minus 0. Now, using equation 18, 19, and 20, we get at half rho u infinity cube dA CPA r omega rho dA u infinity 1 minus a v3. This is 21a. Then we have u infinity square Cp of a r omega 1 minus a v3. So from here we get v3 equals to 2 u infinity square a into 1 minus a by r omega. So that's what at the downstream location, that is here at 3, we get a v3. Now we can now write, since we have a prime of r is v3 of r by 2r omega, which is the radial induction factor, tangential induction factor. So this is tangential induction factor. So what we get, a prime of r u infinity square a into 1 minus a r square omega square, which means v3 is proportional to 1 by r, obviously for a equals to constant, and with the local speed ratio lambda equals to lambda mu r omega by u infinity r omega by u infinity, where mu is r by r. We also have a prime r equals to a into 1 minus a by lambda r square. So we can conclude, what we can conclude is that wake rotates more if the turbine moves relatively slower. That means low lambda, and higher lambda leads to less wake rotation. So lambda is the tip speed ratio. Okay, so that can be connected with this weak rotation. So what you get is that you, if your lambda is low, the turbine moves relatively slower. So which is the case towards the hub. But when you goes towards the tip, which is high lambda, then leads to less wake rotation. So that means close to the hub, where the lambda is low, you have more wake or wake rotates more. That means this rotation of the wake is going to impact more predominantly close to the hub, whereas the impact would be less predominant to the tip because of this connectivity. So this is what we can get a relationship between this wake rotation and all this. Now what we can look at the, so another theory which is called blade element or blade momentum, which is BEM theory. So this is blade element theory or BEM theory, which is very well known in the context of these calculations of the turbine. So we get the annually independent from each other like rotor disc. Okay, and assume the aerodynamic lift and drag accounting lift and drag accounting to 2D airfoil theory. So what we say that the solidity at radius r is defined as sigma r, which is b into c of r by 2 pi r, where b is the number of blades. So the overall solidity is total blade area divided by disk area. We get sigma is 0 to r er dr by pi r square. So that's what we have. So what we have is function of r. A prime is also function of r. So these are already we have. So what we can now, we can see that this is now allow me to have this thing that now we can see how in the context of now, now we can see if we see the, so this is blade element top view at R. So, but if you see, this is how the wind is coming These are the turbine which is rotating. So we have taken a small area here, which is dA, CR into dr. And at this particular small infinitesimal area, the blade speed would be omega into r because it's at the r. So the tangential velocity is a r omega, and axial wind, which is from free steam to reach to this disk, is u infinity 1 minus a. Now, this is the situation where you can see that this turbine which is exposed to the incoming wind, and then if you look at the top view at R, you get this essentially the velocity triangle, and you can see you have the blade velocity here. Okay, you have blade velocity here. You have induced tangential velocity, which is coming from here. This is blade speed, and this is induced tangential wind direction. Here, alpha is angle of attack. That means if my turbines are there, so every turbine aerofoil, this is my wind direction. So the aerofoil angle. So that's what it is shown. And here the effective wind direction is shown like that. Alpha is the angle of attack. Beta is the set pitch angle. At R, and P is essentially alpha plus beta, which is nothing but flow angle. So the axial wind which is coming, that is this one. So that's coming perpendicular to that. So my blade lies leads, then the axial wind comes perpendicular to that, and this is my relative wind, and this is my tangential vector. So once you get an concept of this particular velocity triangle, then it everything else would follow. Simply the calculation around this. So here what you can write, my effective wind magnitude, that is W, which would be, one can write that, which would be U infinity square 1 minus a square. So if I look at that velocity triangle, this is my velocity triangle that I am trying to find out. So this is my W. So this would be using your typical Pythagoras theorem, plus R square omega square 1 plus a prime square. Now 2D lift coefficient, that would be CL of alpha. 2D drag coefficient, CD of alpha, and the area of blade element, that is DAB, which is C dot dr. So what we can find out, lift and drag of blade element. So that now one can find out. So essentially, once you have this velocity triangle understood, then you can find out the lift and drag of blade element. Okay. So we'll continue this discussion. We'll stop it here. Thank you.